Hi, in this video we're going to talk about transformers and how our electrical power grid is set up in Ontario. So what is a transformer? A lot of you don't realize that you've seen one before. They're either those green boxes that are sitting on the ground and sometimes they're painted over to make, it look pretty. Or in Toronto, they are on telephone poles, those little gray cylinders. Typically there's one, but they can stack them up to three or four on one telephone pole. So what exactly do they do? Well, basically they're a device that changes the voltage and current. All right. So a device that changes voltage and current. So why on earth would you want to change a voltage and current? Well, basically a generator generates power and it's going to be set at a certain voltage and current, which is not the same as what you get in your house. And I'll explain all the different voltages and currents later. So it is a device that changes voltage and current, just like an adapter. And it does use Lenz's law. So uses Lenz's law. Okay. And so let's actually set one up so you can see what it looks like. So I'll start on a new page and I'm going to give you an example of a step up transformer. Okay. Transformer. And we're going to step it up by 3 times. So what does a step up transformer means? That means you're going to change the voltage higher by 3 times. But that also means that the current is going to be reduced by 3 times. All right. So step up transformer, generally the voltage increases 3 times, but the current decreases 3 times. The reason why the current doesn't increase is because you can't just make energy out of nowhere. All right. So there's got to be a sort of an equal energy kind of idea. So you can't, it has to even out. Okay, so let me show you how it works. First, you need an iron ring or an iron square. So I'm going to draw a square for you, like so. So an iron ring or an iron square. Okay, so this is your iron ring. And then I'm going to have the primary voltage, and it's going to wrap around one side of the square or the ring. Okay, so let's have it come like this, and I'm going to have 5 loops. So 1, 2, 3, 4, 5. Okay, so 5 loops. Oh, 1, 2, 3, 4, 5. So this technically shouldn't loop. It should just come around here. So this is the last, like so. Perfect. Okay, so 5 loops around this, and let's pretend it is 3 volts. All right, excuse me, 3 volts. Going in, and we're going to have this as 3 amps. So this is called the primary voltage. All right, so 5 loops, and this here is your primary voltage. Perfect. And let's pretend that the current is coming in this way. All right, going around like so, and then out that way. If I use my left-hand rule, again, I'm drawing out electron flow. So I'm going to use my left hand. This here is going to be out in front, and then there's a thumb pointing down. So this is going to be a north pole. Perfect. Now, let's do the secondary loop, right? The secondary voltage here is going to be 3 times higher. To actually change the voltage, what we need to do is actually put in 15 loops. So notice it's a 3 times, or it steps up by 3 times. So this is going to be 15 loops. So let's draw that out and try to draw 15 loops. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I'll stick one in here, 15-ish. Okay. Whew. There you go, 15 loops. And that's essentially how we do it. Now, how does it work using Lenz's law? Well, basically how this works is it has to deal, you first need AC current, all right? So the current's always going to be changing directions. And that's true for generators because remember in the last video, it changes every half turn, okay? And so if let's say this here is a north pole being produced, remember, you have all these tiny, tiny domains in the iron ring, and so it will slowly move towards this loop. Now, since this is a closed loop, it's going to react and try to actually repel this incoming north pole, and so this will become a north pole, and then you're going to have current created around there. All right, so and according to this, that's north, this must be going that way into the loop. Okay, now because there are 3 times more wire, you're going to have 3 times less flow because the electrons are going to have to go through 3 times more wire to get there. And that's why it's a decrease in current, but an increase in voltage because there is more loops that's sensitive or reacts to this incoming north pole that's coming. Again, all due to Lenz's law. Okay, so this here technically is a moving magnetic field. Okay, and essentially the domains, all right, align with the magnetic field, giving the impression of a moving magnetic field towards the secondary coil. Okay, so this is your primary coil here, this is your secondary coil. Okay, and so this here is going to be your secondary voltage, and that's going to be 3 volts times 3, which is going to be 9 volts, and the current is going to be 3 amps divided by 3, which is 1 amp, essentially. Okay, the formula for this, if you are curious, is basically the number of loops in the secondary coil, in this case 15, divided by the number of loops in the primary coil, which is 5, and that will be equal to the voltage in the secondary coil divided by the primary coil. And it's also equal to the inverse of that. So the current of the primary coil divided by the secondary coil. Okay, so that's sort of the overall formula for that. Perfect. So just a brief summary on the step-up transformer. Essentially, when of a current is produced, it will, let's say, produces in this direction, a north pole. The domains line up and it will move, like line up and influence these coils. These coils will feel like there's a moving magnetic field coming, and it will actually react to counteract that moving magnetic field using Lenz's law and produce another north pole. Now, if this was a south pole, then instead of a south pole, then this will be also, producing a south pole to try to counteract that magnetic field. All right. And again, this is all AC current. So the current does flip every half turn. And so then therefore, this will also mimic that, but you're going to have a voltage 3 times more because there are 15 or 3 times more loops to catch that magnetic field and react to it. But because there is 3 times more coil or more wire, it'll be less current. Now, you can probably guess a step-down transformer is going to be different. A step-down transformer, that means you're going to have 15 loops in the primary coil and then 5 loops in the secondary coil, and you're going to make the voltage less, but the current more. Okay, so let's write that as a summary. So step-down current, step-down transformer, not current, transformer. Okay, essentially you're going to have less loops in the secondary coil. All right, and as a result, you're going to have less voltage, but more current. So it's just the reduce. Okay, so let's talk about our power grid. All right. So our power grid, how is that set up? Well, basically, you're going to have the electrical power plant or electrical generating station. And there's actually 2 different ways of turning the turbine. All right. And then I'll show you how transformers are built into the power grid. So there's 2 types. There is your fossil fuels, or nuclear. I'll put them under the same thing. And then there is sort of natural power, okay? So hydro, we call that, and wind. All right, I'm going to skip solar panels. Solar panels are a little different. They produce direct current, and so that will be discussed in grade 12 physics. So we'll just skip the solar panels for now. Okay, so for our power grid, you have either a nuclear generating station or something that burns coal. All right, so the coal or natural gas that's also exists in Ontario. And then you have the hydro, which is falling water, like waterfalls, like Niagara Falls, and then the windmills. Wind and hydro directly turns the turbine, whereas for fossil fuels and nuclear power, they don't directly turn the turbine. So what does that mean? All right. So remember, for generators, you have the North Pole here, the South Pole here. Instead, there'll be big electromagnets. And then you have the coils, okay? And so I'm just going to put like these blades, right? And there's always going to be more than one coil, but you have these blades that rotate. And there is going to be more than one coil in these. Okay, so they're all attached to coils, so you get maximum amount of power generated. Okay, for example, and basically this is your turbine, and they're attached, actually not like this, but I just want to represent, they're attached to the coils which turn the coil. So you have the blades, and then they turn, and that's attached to coils which they turn, but I kind of combine them all at once, right? So this is the turbine. What happens is you have falling water Okay, so the water falls and turns the turbine. Okay, or the wind also does that too. Okay, so wind or water falls and turns the turbine, and because it falls this way, the turbine is going to turn that way. Okay, and that's the beauty about hydro and wind. You're not burning anything. Now, with fossil fuels such as coal, you have to burn the coal and you have to burn the oil. And in nuclear power, what they do is they do a nuclear reaction to actually heat up the water. All right. So both of them require heat. So I'm just going to pretend this is coal. Okay. So here is coal. And for example, and they're going to burn it. So here's my fire. So there's my fire, and I'm going to draw make it all nice and fancy. There's the fire, like so. Hey, that's not bad fire. Now, what do you do with that heat? So either coal is going to be heating up, or nuclear fission also it produces heat. So what does that do? That's going to actually cook the water. All right. We got to cook something because, we're not making any energy yet, but we're going to cook water. So here is H2O, and that's going to produce steam. Okay. So this is going to produce steam. And guess what? Steam is going to turn the turbines. Can you believe that? Yes. Rising steam turns the turbines, okay? So basically you're going to have the turbines here, and I'm just going to draw them a little smaller. Okay, so here is your north, and here is your south. This is totally not to scale, but here's your turbine, and it's going to turn the turbines. And there's your coils in there. And the steam actually technically does that. All right, I'll draw that in. There you go. Kind of idea. So the steam turns the turbine. So kind of like steam pressure kind of idea, like a pressure cooker. Okay, which is totally inefficient in my opinion. So this is way more efficient because the power is directly turning the turbine. Here you got to heat the water, which heats the steam, which turns the turbine, and then you got the generation going. All right, which is very, very inefficient, but hey, that's what we can come up with. And that's why renewable energy like this, or sustainable energy, is what we're trying to find or solve our energy problems. So the next step is, how much energy does this generator typically generate? Well, all generating power stations typically generate about 20,000 volts. Okay, so this is from your generating station. Generating station. And this is where the transformers come in. Okay, so this is how much voltage from your generating station. And what they've discovered is that if you actually increase the voltage in your wire and decrease the current, you'll actually save be able to transmit more power. There'll be less power loss. Okay, so how do I know this? Well, remember, power from grade 9 electricity is equal to the current times voltage, for example. And you know Ohm's law is equal to I times R. I'm just going to rearrange it so the current is voltage divided by R. Okay, I'm going to sub that in there, and this is what I'm going to get. This is going to be power is equal to V squared over R. So I'm replacing the I, okay, just so you know. So the power can be conserved, or more power can be transferred if you increase the voltage and decrease the resistance in the wire. So essentially, after the power is made in a generating station, it goes through a transformer. It is a step up transformer. Okay, and you'll see that in right by nuclear generating stations, especially nuclear ones and coal plants. You'll see that picture there with all the transformers. Okay, and it will step it up to 5,000 kilovolts, which is a lot. And then they're going to transfer it to the wires, okay, the hydro wires. So now we're in the hydro wires here. Hydro wires. They typically look like this, okay? And then once it gets to your house, you can't have 500 kilovolts of energy in your house. So that's a lot. Typically, your house has 240, all right, and your outlet has 120, all right. So you need a step down transformer, step down transformer, okay, and they have a station. So this here is a typical station that you would see in your neighborhood. And then they have another step down station or green box in your neighborhood, and then it goes into your house. And by the time it gets into your house, it's only 120 volts. Okay, and that's why we have those transformers, because it's able to change the voltage in such a way it can transmit power and it doesn't lose energy. All right. And that's it. That concludes our electromagnetism unit. You know how to have electricity to make something move like a motor, and now you know how to move something to create electricity like a generator. All right, see you later. Bye.